going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about synthesis of porous silicon. So, that silicon materials commonly used for electronic device. So, we will discuss about porous materials, so what is called porous materials. So, different type of pores naturally available or we can also prepare in labs. So, that we will discuss, and then porous silicons, that particularly that materials we will discuss, and how to make silicon porous experimentally. So, in lab scales by considering an experimental setup. So, there we can consider silicon precursors or and using that we can develop the pores by many methods are available. So, out of that electrochemicals etching method that will be discussed, and then some mechanisms of pores formation. So, once we take silicons and make the pores in that particular materials, the pore formations depends on mechanism. So, means that we will discuss, and then different factors that will be affected when the pore formations is there. So, by controlling these parameters, substrate type, doping level, concentration of HF, current density, effect of lights, durations of etching. So, these are the various parameters we will discuss when we discuss about the electrochemical etching methods to develop pores in silicon materials. So, then for morphology of these silicons, different structures that we will discuss. Okay. So, let us start. So, the materials with the pores normally whenever we synthesize any materials, so that materials consist different type of pores, that pores dimensions may be nanometers to micrometers. So, within that range. So, depending upon the type of materials and method of synthesis by which we are preparing that porous materials. So, if the depending upon the pore diameters, we can classify the materials into micropores, mesoporous materials and macroporous materials, the pores that would be developed inside of the materials during preparations. If the diameter of the pores is less than 2 nanometers, so then we can say the material is porous materials, and if it is 2 to 50 nanometers, then we can say it is a mesoporous materials, that materials we have developed. So, once we prepared, and then we can characterize for a particular characterization techniques to measure the pore of that particular materials, and based on that we can say that. Also macroporous materials. So, in macroporous materials usually having pore diameters more than 50 nanometers. So, here few examples I am showing. So, that is naturally available, or also we can prepare, so that is called man-made porous materials. For example, see here these are the man-made materials and this is natural materials. So, we can naturally it is available. So, this synthetic or means in labs we can also prepare different type of porous materials. So, that materials would be porous, that depends on that whether it is we are preparing by using purely organic materials. So, if we use organic porous polymers means organic materials as a precursors to develop organic porous polymers type of materials or composite that consist of pores. So, or maybe purely inorganic. So, different silica, one of the example is there silica SiO2. So, that is also purely inorganics and consist of various type of pores. Alumina also is another example of purely inorganic metal oxide. So, that is having pore consist in that particular materials. Even so, hybrid material, that is organic and inorganic precursors, both we can use to develop a particular porous materials, for example MOFs. So, these are the examples, and when these materials, I said different materials it is available naturally or synthetically lab we can prepare these porous materials. So, activated carbon, silica, zeolites, MOF, these are the porous materials. These porous materials, why you are interested to develop or synthesize these porous materials, these are the materials having highly pore and high surface areas. That surface area sometimes is useful for a means particular applications when high surface area is required. For example, in reaction engineering or chemical engineering point of view, when we prepare any catalyst, so then support materials sometimes we have to use or prepare that having highly porous materials, that may be activated carbon, silica, zeolites, MOFs. These are the materials we usually use. Sometimes it is as a catalyst material, sometimes it is as a support materials. So, these are the trade names or the way it is expressed. So actual materials is this type of. So and the surface area, you can see specific surface area, that very extremely high surface area means 896 meter square per gram materials for activated carbon. So also 1149 meters, depending upon that same materials different way you can prepare, and based on that surface area also would vary. So and next is that if we micro scale or nano scales, and that pore, the whatever the pore that is forms, that is highly distinctive features for this particular porous materials. So pore is important, whether the pore is micropores, mesopores or other type of pores. So that pore structures impart material with high specific surface area, that already have discussed. So once we develop high surface specific surface area in that porous materials, whatever we synthesized, once example I said, it can be used as a support material for the catalyst when it is used for the any reactions. So then that role of that materials not only increase the surface area, once it is increase the surface area, that would enhance the mass transfer efficiency, means so when reactants is come in contact with the surface of the catalyst. So there's means diffusions or transport of the reactant from the bulk to the surface of the catalyst or active sites of the catalyst, that is very important. So that is also controlled, or that will increase once it is having high surface area of that materials we are using. Therefore, interfacial interactions between the surface material host materials, so where the catalyst or active sites are distributed, and with the reactants or the surrounding environments, that will means affect overall performance of the materials. Therefore, the means material performance, one it is improve or change. So then we can develop better materials, and that would be good for industrial applications, and widely that would be used. Okay. So now here fabrications process of the porous materials. Here we are saying that framework porous materials. Here few examples I am showing, small of materials, metal organic frameworks or covalent organic frameworks. This is framework type of porous material. So here some framework structure formations is there, that can be means that way we can prepare that material. Another is mesoporous materials. One example is SiO2, and that can be prepared by using some soft templates. So and silica precursors that can be used to prepare this mesoporous structural materials. So and then hard template based microporous materials, that also can be synthesized by using silica or other materials, that is metal oxide. So that is can be used, and at the for the preparation of the porous materials, and at some stage or in the different steps and multiple steps we have to follow to prepare this hard templating method. And after that, in the process in one steps, that template we can remove from the material. So by which it can means the remaining portion of the material, that is metal oxide remains, that is metal or metal oxide whatever, that would be highly porous, the pore structure should be developed. So here you can see for the preparation of the MOF of type of materials. So initially you have to take ligand and ions. So metal ions we can take any as a precursors, that which particular metal, that depends on that particular MOF we are preparing, that may be cobalt, iron, nickels or any other metals, copper, and ligands, that is organic compounds we can use, that we will discuss later. So then this type of means metals, different metal ions, that would be linked with that ligands, and then this type of frameworks formations is there, and then mesoporous type of materials. So here we have to say take, if we want to prepare silica, then silica and precursors, tetraethyl orthosilicate like of precursors we can take, and with that some surfactants we have to use. So many surfactants are there available in open literature. So cationic, anionic or neutral, any surfactant we can take. So detailed methods already have discussed, and after that this type of structure formation is there, and then we can remove that surfactants and mesoporous. These are the pores, and this is the SiO2. You can say that type of structure formation is there. As a result, once that template is removed from these sites by calcinations or high temperature oxidation, so then highly porous or pore development will be there, and pore dimensions we can measure, and based on that we can say whether it is mesoporous or any other type of pores has been developed, and once this type of highly porous materials we are able to develop, that also can be used as a hard template, means for the next preparations any precursors we can use, and that would be distributed this mesoporous solid or silica, and then this type of frameworks will forms, and after that we can eliminate or dissolve, this is you can say SiO2 let us say. So, after that if we remove that SiO2, so then spore will be developed, and this type of let us say this is palladium nanoparticle. If we prepare by using silica as a hard template, and then we can remove by using strong base we can use to remove this, and then this type of pore will be developed. Okay. So, now basic about the porous materials we have discussed. Now we will discuss about detailed porous silicons materials, from how to prepare that, and actually these porous materials or silicons. So, from electronics or computer systems, from that point of view it has importance. So, that is widely used different type of IC means preparations, transistor preparation, diode preparation. So, that usually used. So, also some semiconductor materials also, sulphide, different type of sulphides, these type of materials also available. So, that also can be prepared. So, here basically we will discuss about porous silicons. Okay. So, that having this type of materials having optoelectronic properties. So, optoelectronic applications these materials usually use, and this type of materials due to their nanocrystalline natures in the pore walls, this type of materials usually or most commonly used in optoelectronic applications materials developments, that is the application. So, also fluoroluminescence properties is observed at room temperatures, therefore, this type of materials very good semiconductor type of materials. So, these are used, a lot of applications is there. So, here one image is showing, that is porous silicons. These materials once it is synthesized and then it has been taken that image. So, here also that pores structures in that materials, here the different type of pores present. So, that pores we can control or develop depending upon the method of synthesis. So, we have used. So, here's black means ones are here's this silicon, and the pore here you can see rectangular type of pores is there, and here cylindrical type of holes as a pores is present, and from here A, B and C, three different type of cylindrical pores you can see. So, here porosity is very less, means 25% porosity, here little bit higher porosity means 50%, and then it is 80% porosity. So, as per the experimental data it is showing. So, means the porosity that we can control depending upon the materials we are using, the surfactants means at what temperature we are heating up or concentration of the materials, depending upon that we can synthesize different type of porosity. In the right hand side rectangle type of pore has been developed, and pore percentage porosity also means 25-50% porosity, 80% porosity, depending upon the method of synthesis we can change the porosity. So, now question is how we can make that silicons porosity, means pore we can develop in that particular materials. So, electrochemicals method or electrochemical etching methods is there, that methods we will discuss. There are other methods is also there. So, out of that only electrochemical etching methods that will be discussed. In this particular method hydrofluoric acid, nitric acids are used, and one electrochemical cell is used, where silicon as a electrode materials that will be taken. So, here single crystalline silicons, that wafer we have to use to prepare porous silicons, and HF that is used as etchant materials. So, chemicals that you have to use. So, this is here you can see graphite electrode that was taken, and here's p type silicon wafer that was taken, and in that solvents that was used hydrofluoric acid, waters or ethanols. P type silicon wafer was taken to make that silicon porous. So, here's also the same diagram electrochemical cells. So, here you can see silicons this orange color is silicon wafer that was taken, and similarly HF solutions that was taken and P type silicons. Here electrode was taken different, platinum or graphite, either ones we can use. So these are the things we can use, and current, low voltage we have to use, and this is the solvent category, means HF waters, and the silicons, that substrate we have to take, either it may be P types or N type silicons we can use, and some doped materials also may be present there. Okay, so when hydrofluoric acid that acts as electrolyte, so that was taken or etching materials. So here's the pore size that would be control 1 nanometer to few micrometers, so that can be controlled depending upon the current density, means dopant types, concentrations, wafer orientations, electrolyte composition. So depending upon that, the surface, the pore that would be forms inside of that silicon wafers, there's the size of the pores that may vary, and we can control by controlling the current density, dopant types, dopant concentrations, wafer orientations, and electrolyte compositions. Okay. So I said the dopant types and P types, N types, so the silicons that we take as that may be P types or N types we can use, that also influence the valence bands and hole availability, that will affect the pore formations as size as well as pore size as well as number of pore formations. Okay. Depending upon the type of dopants materials have been used in that N types or P types silicons, that depending upon that dopants it would be either N types or P types, and depending upon that different type of holes formations and the hole formations and its size also would be controlled. Okay. So when in electrochemical cells we are taking HF solutions and silicons wafer is there, this type of reactions might be there when silicon in anode, if we take silicons and then SiF4, SiF6 type of reactions, means silicon, this zero oxidation state and fluorides may be ionic state that is present, and then there is a hole creations, and that here I am showing that mechanisms how that is formed actually. So in cathodes usually either platinums or graphite I said, so that we can take, and anode materials I said that silicons that we have to take at anode materials, and when suppose and when it is taken as anode materials and some voltage and current will be passed, then electrons release, there is a release in electrons, and for a therefore means some hole formations would be there in that wafer, and after that so hole will be the holes whatever that would forms over the surface of that silica wafers, then hole can migrate to some one region to the another regions, and by that way means here you can see, so this is the holes and this is the silicons and fluoride ions is present. So that may react, means this type of reactions would form, SiF2 means species will forms, and then against this SiF2 further react with HF that is present in that solutions. So SiF4 would forms and further against that would react with the hydrofluoric acid that is present in electrochemical cell, and at this 2 SiF6 formations is there. So here the mechanisms you can see, silicons that is Si, fluoride ions that is attacked here due to the hole formations when in some voltage and current we are maintaining in between two electrodes and electrochemical cells. So then that fluoride ions that would be attacked in that hole that is developed in that silica, and then one by one fluoride would be substituted, means attacked over the silica, and H would be it would interact with the silica, and one by one it would be replaced by fluoride ions, and then SiF6 means this is the multiple step process, one by one fluoride will be interact with that holes, and by that way SiF6 2 minus ions formation is there. And sometimes I said when H2 SiF6 that would forms, that would be dissolved in the electrolytes, and that whole formations means started, that is the beginning actually. So initiations by pit formations, initially pit formations would be there, and from there pore formations will start. Okay. And then these pore formations, actually if we said that there is the current and HF concentration, that is the things we can control, means low current or high current we can use for these electrochemical cells. HFs that is would be used, that also we can control concentration, either it is low concentration or high concentration. Depending upon that also pore structures will develop in that silicon, that materials we have taken to develop the pores. If current density is increased beyond a certain value, so more means number of holes formations would be there at a time, and also means when high current density we are using, so there is a possibility of means oxidation reactions possibility is there, that will decrease down the performance of the system. So means surface oxidations possibility is there, SiO2 that may forms above the surface, means by this type of reactions, means hole is there, silicon wafer or silicon element is there. So this type of hydroxyls means ions formations is there due to the high current if we use, or current density if we increase beyond a certain value, so then generate more holes at a times, and there is formation chances of formation of surface oxides. Okay, so that may increase. So means against that also this reactions is also reversible. So against SiO2 react with HF, and then H2SiO6 formations is there, that may forms, but it is not desirable to forms when we are preparing silicons porous. So okay, so or it is called polishings. Okay, so means whenever we are means preparing the silicon, so that can be used for electronic device. So it has some optoelectronic properties, that optical properties of that porous silicons that are found to be unstable after their formations, means this type of things we are not expected when means silicon would means converted into porous silicons. So we try to maintain at low currents, or current density should be as low as possible. So next is the pores. So various type of pores, means when pores will be developed above the surface of the silicons, different type of pores may forms, that irregular, regular types, closed types, open types, penetrating or ink bottle types. So these are the different type of actually geometry that have been considered, or based on different study that has been proposed, that different type of pore structure or type of pores may forms during pore formations over the surface of silicons. So next is the factors that affect the porous structure of the silicons. So here I said substrate, either it is P types or N types, that depends also the elements we used with the silicon. So depending upon the dope materials, so either it is P types or N types. So materials with the depending upon that also we can develop different type of means depending upon the substrate type. So the pores also will affect. Okay. So let us say very high concentrations of holes is present, means the silicon wafer that we are considering 4 different types of silicon wafers that we can form or we can consider. So either very high concentrations of holes, or maybe low concentrations of holes, or maybe high concentrations electrons or low concentrations of electrons. So either in terms of electrons or in terms of holes, this is in terms of electrons and this is in terms of holes that is present, either it is high concentrations or low concentrations of holes, or high concentrations of electrons or low concentrations of electrons, means different type of means holes that is present in the silicon wafer, that depends on the dope, either it is P or N types. And also next is the concentration of HF that is used in that electrochemical cell as a electrolytes. HF concentrations is also very important, that also affect the pore formations over the silicon wafers. So if we increase and decrease the HF concentrations, means in electrochemical cells we can either increase the concentration or decrease the concentrations. If decrease the HF concentrations, so then the pore formations may increase, means that what concentrations we are using. So depending upon that, pore means formations either increase or decrease. At low HF concentrations, the pH of the solutions will increase as a result, means that would help to promote the pore formations. Okay. Next is the current density or voltage, that is used during the etching in the electrochemical cells. Okay. At large current density, electropolishing that will take place. So, that is not desirable. So, we should avoid that one. Actually, electropolishing, that is oxidations, over oxidations, silicon dioxide formation. So, when we use large currents, that possibility or electropolishings that will take place, and porous structure that forms only low voltage and low current. So, that is actually desirable, means current in terms of voltage and current. So, whenever we make any silicon wafer into pore, means good pore developments for optoelectronic applications, there's low voltage and low currents that we will try to use. So, here actually this is the transition. So, here's regions where the current and voltage that we can use to make the silicons porous. So, porosity gradually increase, and up to this it is transition regions depending upon that much current and voltage that we can use, and after that if we increase the voltage, then electropolishing possibility is there. So, effect of light, next is the another parameter, that is effect of light. The chemical reactions can often controlled by using lights. So, when electrochemical cell we have taken and current voltage we are passing in that HF electrolyte that was taken in that cell, electrochemical cell, their reactions will take place, chemical reactions for making the holes in silicon wafers. So, sometimes that is controlled by the lights that we use. Okay. Appropriate wavelength of lights that is fall in that materials, it generate more electrons hole pairs, and that also will affect somehow in pore developments. Then durations of etching. So, the reactions will take place inside of the electrochemical cells. If it is longer period of times, if we wait for, means the reactions will take place, then smaller are the formations of nanocrystalline silicons, means a smaller amount of nanocrystalline silicons formations would be there. So, longer time is also good for formations of means porous silicons. So, okay, so etching time is very important. Okay. This is the ACM image of porous silicons. The morphology you can see. So, this image means once it is made the pores inside of that particular silicons, and after that the image was taken. So, you can see different type of pore formations is there. So, once we can analyze the pore diameters, so we can see whether it is micropores, mesopores or macropores, that also we can checked by using a particular characterizations. Okay, so thank you. Today is up to this.